Hello friends, in this video I am going to solve exercise question from book Topics in Algebra. Question is, let G be a finite group whose order is not divisible by 3. Suppose that AB cube is equal to A cube B cube for all elements AB in group G, then prove that G must be abelian. Note that order of group is number of elements present in that group. Before starting our proof, we will recall definition of an abelian group. So, a group G with a binary operation dot is said to be abelian or commutative if for all elements AB in group G we have A dot B is same as B dot A. So, proof: define a map phi from group G to group G such that phi of G is equal to G cube. Now we will show that this map phi is an isomorphism. For this we need to show that phi is a homomorphism and 1 onto map. So to prove phi is a homomorphism, consider any two elements, say G1 and G2 in group G. Then we have phi of G1 G2 is equal to G1 G2 cube. Now by the condition given in the question, we have G1 G2 cube will be equal to G1 cube G2 cube. Now G1 cube is phi of G1 and G2 cube is phi of G2. So finally we get phi of G1 G2 is equal to phi of G1 phi of G2, and thus phi is a homomorphism. Now to prove phi is 1 we will use the theorem. A homomorphism phi is 1 if and only if kernel of phi is singleton identity. So to prove here kernel phi is singleton identity, consider any arbitrary element, say G in kernel phi. Then phi of G will be identity by definition of kernel. Now phi of G is G cube, so we have G cube is equal to identity. Now if this thing will happen, we must have G equals to identity, because if G cube is identity, then order of G will be 3, and this implies order of the cyclic group generated by G will be 3. Now cyclic group generated by G is a non-trivial subgroup of group G. Then by Lagrange theorem, order of cyclic group generated by G, that is 3, will divide order of G. But in the question it is given that order of group G is not divisible by 3. So we must have G equals to identity element of a group G, and thus for any arbitrary element G in kernel phi, we have kernel phi is equal to singleton identity, and this proves that phi is 1. Now clearly phi is onto, because for any element G cube in G there will exist an element G in G such that phi of G equals to G cube, and thus the map phi from group G to group G is an isomorphism. So after this we can conclude that every element in group G can be uniquely expressed as a cube of an element in G. Next we have for all elements AB in group G, AB cube is equal to A cube B cube. This is the condition given in the question. Now this LHS can be written as AB 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 3 times, and A cube B cube can be written as A B B B. Now cancelling A from both left side and B from right side, we get BA is same as AA BB. Now BA can be written as BA square, and AABB can be written as A square B square. Call this expression as star. Now for all elements AB in group G, AB to the power 4 can be written as AB square its square. Now from star we have AB square will be equal to B square A square and its square. Now again if we consider B square as an element in G and A square as an element in G, and again applying condition star, we have A square its square, B square its square. Now A square its square will be A to the power 4 and B square its square will be B to the power 4. So finally we get AB to the power 4 is same as A to the power 4, B to the power 4. Now again this can be written as AB, 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 AB 4 times, and A to the power 4 will be A 4 times and B to the power 4 will be B 4 times. Now again rewriting LHS in this form, RHS as it is. Now BA, BA, BA 3 times can be written as BA its cube, AB as it is, and RHS as it is. Now again BA cube will be B cube A cube from condition given in the question, and this RHS as it is. Now B cube will be B, B, B 3 times, and A cube will be A 3 times, AB as it is, RHS as it is. Now cancelling A from left side and B from right side, we get this expression. Now again this B 3 times can be written as B cube, A 3 times can be written as A cube, and from RHS we get A cube, B cube. Now as this AB are elements in group G, so A cube will be again an element in group G and B cube will be again an element in group G. So call A cube as G1 and B cube as G2. So this expression can be rewritten as G2 G1 is equal to G1 G2. Now as this G1 and G2 are any arbitrary element in group G, and for any arbitrary element in group G we have G2 G1 is same as G1 G2. So by definition of an abelian group, our group G must be abelian, and this proves our result.